Welcome to the Consulting Specifying Engineer Webcast, HVAC, Hospitals and Healthcare Facilities, sponsored by Egis and Carnes Company. I'm your moderator, Amara Razgis, with Consulting Specifying Engineer and CFE Media. Here are some tips for today's webcast. If you're having trouble with your slides or sound, refresh your browser or click on the Refresh Media button directly under the presenter's photo. You can control the volume settings by adjusting the volume on your computer. If you are having technical problems, click on the question mark at the top right corner of your screen to bring up a list of system checks to try before contacting an online technician. If you do need a technician, type a message into the Ask a Question box and someone will respond as soon as possible in the Answered Questions box. Type questions for today's expert presenters in the Ask a Question box on the left side of your screen. The Q&A portion will start after the prepared presentation, so that will be in about 45 minutes. If you are on Twitter, tweet your questions to us at #CSEHospitalHVAC. Today's webcast is being recorded, and you will receive an email with the link to the archive in about a week. To download the presentation slides, use the event resources on the left side of your screen. For those of you who are interested in receiving one AIA CES approved learning unit for this event, you need to pass a 10-question exam. To take the learning unit exam and to download your AIA CES certificate, use the Learning Unit Exam tab option at the top of your screen. The exam will open in a new browser window, so if you want to take the exam after we're all done, I suggest you open it right now because the link will break when the webcast signs off. The exam will also be posted on the Consulting Specifying Engineer website with the on-demand version of this webcast. In keeping with the American Institute of Architects Continuing Education System Policy, please take some time to read the quality assurance slide. Here's a list of the learning objectives for today's webcast. We'll touch on these in today's presentation. Please note that any blue underlined text that you see in today's presentation is a hyperlink to a reference or a resource. Now we'll hear from today's sponsors. At the conclusion of the commercials, you may experience a few seconds of silence to make up for varied internet speeds. Please stay tuned after the videos for today's presentation.
VFDs can save 30% or more in energy costs, but VFDs can damage motor bearings. Without shaft grounding, VFD-induced voltages can discharge through motor bearings, causing damage such as pitting, frosting, and fluting, and unplanned motor failure in as little as 3 months. Egis shaft grounding rings provide proven long-term protection against VFD-induced bearing damage. By channeling harmful shaft currents away from bearings and safely to ground, Egis rings ensure that motors last for the full L10 life of their bearings. And while you can install Egis rings yourself or have a motor repair shop install them, the easiest way to protect your motors is to purchase them with Egis rings factory installed from any of a growing number of motor manufacturers. To protect VFD motors, always specify Egis rings. To learn more, visit the Egis website and schedule a lunch and learn worth 1 hour of professional development.
In a forever-changing world more focused on health, well-being, and energy savings, Carnes realizes the challenges and consequences that impact health and comfort across the world. We are continually making strides with technological advances to deliver a positive and significant impact on society. People are the heart of our focus. They are what drive our innovation. As buildings become more airtight due to better construction methodologies, the need for increased and balanced ventilation is critical. Without it, internally generated contaminants accumulate and cause deficient indoor air quality, which leads to significant health and cognitive problems for occupants. Deficient indoor air quality is a serious problem, especially considering on average, Americans spend 90% of their time indoors. For nearly 60 years, Carnes has been dedicated to providing and promoting effective and sustainable energy recovery ventilation solutions. Carnes has been a pioneer in enhancing indoor air quality in commercial and residential buildings of every size. Our ERVs are competitively priced, simple to install, easy to use and maintain, have a quick payback, and enjoy the industry's best warranty with the lowest claims due to long-term reliability. Carnes plate systems provide more health and reliability benefits to the customer. At Carnes, we are constantly pursuing the most efficient human health and comfort solutions to meet the world's energy recovery needs.
Now I would like to introduce today's expert presenters. Jeremy Jones is a healthcare project manager and market leader for Affiliated Engineers Incorporated. He has spoken at the ASHRAE PDC Summit, and he has extensive expertise in the design of healthcare projects, including everything from small-scale renovations to the design and construction of large greenfield hospitals. Corey Duggan is an energy modeling wizard at TLC Engineering Solutions, where he provides building performance simulation and has a wide array of other HVAC knowledge. He is a principal in the TLC Engineering Solutions Peak Institute and a member of the Consulting Specifying Engineer Editorial Advisory Board. All right, Corey, it looks like you're kicking off today's session.
Thanks, Amara. Today, Jeremy and I are going to start off by looking at notable healthcare codes that you should be concerned about in the design of healthcare facilities, specifically with an emphasis on the energy efficiency of the HVAC systems, and then also codes that are very specific just to healthcare.
All right, so the first one we're going to talk about today is ASHRAE 90.1, and that's a standard that will govern the energy usage of your building. It's not specific to healthcare by any means, but it's important to understand because healthcare is a huge user of energy, probably second only to restaurants in energy density. This will govern pretty much all the projects that you will deal with. It's new constructions, major additions. If you're replacing an air handler or a chiller, it governs all of those. It's not retroactive though, so it doesn't retroactively apply to any of your hospital facilities, but new projects it will. The exclusions probably won't apply to any of your projects. It's really just for residential or historical buildings or shacks that don't use any energy at all. Generally, it covers the building envelope, which would be the insulation for an exterior of the building, glass details, things like that. The HVAC system, which is what we're talking about today, but really anything that uses power. The entire document's about 300 pages, and the user manual is almost twice that, so it's far more than we can talk about today. But we'll hit the highlights today, and if you have any follow-up questions, please send them in the tool. Generally, there are 3 compliance paths. The first one you probably will never run into. The simplified path is only for very small buildings with a single HVAC zone that typically doesn't apply to hospitals. So you'll have a choice between compliance path 2 and compliance path 3. It's really up to you. It depends on the parameters of your project and what you and your client are more comfortable with. The prescriptive method is literally a checklist of items that you need to meet. If you choose this option, you have to comply with 100% of those. It's parameters like the efficiency of each piece of HVAC equipment, certain control sequences, the amount of damper leakage and duct insulation and wall insulation. If you comply with all of those, you fill out that form and you comply with the prescriptive method. But if there are any on that list that you can't, you need to go to the energy cost budget option. Or if you're just more comfortable with energy modeling, you would go to the energy cost budget option. In this option, you will go through a tool that will determine the budget of energy usage that your project has, and then you need to do extensive energy modeling to prove that you're under that limit. One important thing to keep in mind is that authorities having jurisdiction vary wildly in the rigor with which they enforce this and review this. It's worth understanding, it's worth getting a handle on the way your individual authority handles this. Sometimes they just want a paper copy of a checklist, and sometimes they go into extreme detail on your calculations. You just should be ready for that. But really, you have your choice of option 2 or option 3 depending on the parameters of your project.
Yeah, that's really good advice about talking to your AHJ before going through the energy cost budget method, because Jeremy's right, it does vary widely, so you really want to know what they're expecting. So the next standard we're looking at is the 2018 IGCC, or ASHRAE Standard 189.1 2017. This is a little bit different, but does have some overlap with 90.1, where 90.1 is typically the base standard that your typical energy codes are adopted around, or the same version of the IECC adopted as part of the I codes. Standard 2018 of the IGCC is more of a green construction code. It's more holistic than just energy efficiency in the way 90.1 is. So it's typically adopted in areas as a stretch code. So something that you could do possibly to get incentives, go beyond the minimum just code requirements here. And it goes into more detail about water efficiency and other items that maybe aren't addressed in your typical building code. Now, what's special about this 2017 version, or 2018 if we're talking about the I codes, is that previously these two standards were completely developed separately from one another, in the same way that the IECC is developed completely separate from ASHRAE 90.1, even though they do have many similarities. So the industry saw that there was an issue in the use, adoption, implementation of this standard, and so ASHRAE, the International Code Council, and the USGBC decided to cooperate and create one combined version of this standard, so that now it can be used as a codified language that can be adopted while still meeting all of these separate requirements. And so it's interesting now that we now have one standard that is published together. So there isn't a separate 189.1 2017 anymore. It's just the 2018 IGCC. And the USGBC's part of that is they wanted this standard to be able to align with LEED, so that you no longer have to ask the question that, okay, well, if I'm meeting code and I'm this much better than 90.1, like how much farther am I from a LEED certified building, or what would I have to do there? And so part of this is aligning with the credit categories in LEED. So this goes into some of the site credits, like I said, the water credits, material things that are part of LEED in trying to create a more high performance building, but aren't necessarily addressed in your basic building code there. So you're really getting more in the ability to build a building that is higher efficiency and closer to be able to get a LEED certification just by meeting this minimum standard. So today, we really have an emphasis on healthcare, though, and we would be remiss if we didn't bring up this relatively new standard. It is in continuous maintenance. I believe this is the second version, and they are in the works of publishing the third version. But this standard is probably largely unknown, I would suspect, to most of you. But if you work on healthcare facilities, or whether that be in design or maintenance and maintaining them, this is really something that you should be aware of, because it is adapting the language from 189.1 specifically to healthcare facilities. So we're talking about that this goes into detail about energy improvements that have specifics to do with the types of equipment and codes that have to be applied to healthcare facilities. Because I know that a lot of people get frustrated with some of the other codes and feel like that really these types of facilities and their very specialized requirements aren't handled really well, that they don't have the proper exceptions for things that they feel like the standard is requiring them to do, but maybe realistically doesn't make sense for that type of building. So this has those sorts of specific exceptions that I think you'll find make a lot of sense. for healthcare facilities. And because, like Jeremy said, healthcare facilities are, our first or second highest energy intensity building type, it's really important that we pay attention to optimizing the efficiency of these facilities, because that has a lot to do with the cost of healthcare and operating them, as well as the care that you're able to get in people who are working there and getting their care.
So ASHRAE 170 might be the most important healthcare standard that you need to be aware of. It'll govern almost all aspects of the ventilation of various room types that you'll see in a hospital. It'll govern things like the pressure relationships you have to maintain between rooms, the minimums for the total air changes and the outside air changes. It defines spaces that you have to exhaust 100% of the time. The current version is 2017, but there were prior editions in 2013 and 2008. And if you live in an FGI state, your FGI automatically references and adopts ASHRAE 170. So that's almost all the states in the country, but even the ones that aren't are somewhat patterned on ASHRAE 170. So it's worth understanding that. You need to check the version of FGI that your state adopts, because if it's a former version, it may not be caught up with ASHRAE 2017. It covers almost all of the room types that you'll run into in a given hospital. There will be some rooms, especially more modern rooms, that just won't be covered, like linear accelerators or high-dose radiation or an intraoperative MRI, some type of room like that. In those cases, you need to start with your own judgment, but still confirm it with your state health department, just to make sure that you're interpreting the requirements accurately. It's been, every time it's updated, it adds new rooms, and that was one of the biggest updates in 2017. But you still need to check if you have a specialty room type. One column to be particularly aware of is the recirculated by means of room units column on table 8.1 on the chart. This will govern the types of systems that you're able to use. So if the answer is no in this column, it's like an operating room or an ICU, you're not able to use recirculating type systems. And we'll talk about some of those today, but an active chilled beam, for example, would not be an appropriate system for an operating room, because recirculation is not allowed in that room. Another key item to keep track of is there are humidity requirements and temperature requirements side by side in this chart, but they're interpreted differently. The humidity requirements are true minimums and maximums. If it says 20% to 60% relative humidity, you're not allowed to go outside those boundaries. If the room is 70% humidity, you're out of compliance. The temperature requirements, on the other hand, are different. They're not absolute maximums and minimums. They're ranges that your system must be able to hit while staying in the humidity range. So the operating room temperature range is going to be, on the chart, is 68 to 75, but I've never met a surgeon that's happy at 68. They always want it colder than that. The fact that the chart says 68 to 75 doesn't mean you're not allowed to go below that. It means that your system has to be able to hit that range. But just keep in mind that you're allowed to go out of it, and will often be required by user requirements. There's an extensive footnote section at the end that you really do need to read through and be familiar with, because it clears up the ambiguities of the chart. And be sure to stay on top of the addenda. There were several addenda issued to ASHRAE 170 2013. And all of those were incorporated in 2017, but once they're published, they're part of the standard. So I don't think there are any addenda for 2017 yet, but there will be, and they will also be binding. Those are free to access on the ASHRAE website, so you can always go and check. You should do that at the start of every project.
Now, this is not an exhaustive list, but is the most commonly considered HVAC systems in the design of healthcare facilities. Jeremy and I are going to briefly describe each system and its benefits and drawbacks when being applied in a healthcare occupancy. Then we're going to go and do a deeper dive into a particular system type with a case study from each of us.
I would say also on this list, it's important to realize that these aren't even necessarily mutually exclusive. You could have cogeneration in your plant or heat recovery chillers in your plant and your spaces would be one of these other room types. So they're not intended to be mutually exclusive either. First, we'll talk about our VAV and constant volume systems, which are probably the most common that you'll run into. I'll use the same graphic to talk about both. VAV system, you send air into the room and it varies depending on load. The minimum will be the minimum code required air changes probably coming from ASHRAE 170, and the maximum would be whatever the load in your room demands. If you have a lot of glass, if you have a lot of occupants, the actual ventilation quantity may be higher than the code minimum, but it would fluctuate between those during the day as the load changes or during seasons as the load changes. If the load drops below the minimum requirement, then reheat coil, electric or hot water reheat coil, will then kick on and modulate the load from there. And all of that air gets returned, or a significant portion of that air gets returned back to the air handling unit, filtered, cooled back down, and recycled. In a constant volume system, the main difference is just what it sounds like. The air quantity you send to the room is constant all the time, and all of the modulation is done with the heating coil. So the room would be sized at the maximum load, and then the heating coil would trim that down when you're below your maximum heating load. The only real advantage to constant volume is that it's simple and predictable. And once your room balance is set up, it stays there unless unless a piece of equipment goes out of control. The big drawback of it is that it is extremely energy inefficient. You're always simultaneously cooling and heating unless you're at absolute peak load, and over time that is a tremendous waste of energy. So that's the primary reason that you would go with a VAV system over a constant volume system. Even though constant volume is simpler and has less moving parts, it's just a tremendous energy waste.
The picture above depicts a ground-coupled water source heat pump system, or commonly known as a ground source heat pump system. But they could also be used with a cooling tower and a boiler rather than a well field. The well field is typically the large first cost item that makes or breaks looking at these systems. So if that's something you can eliminate, it might make the system more viable. Something that's commonly being done to make them more viable is doing a hybrid system where you have wells for, say, 70% of your load, and then for that other 30%, you put in a small cooling tower or boiler that doesn't run as often, so that you're not having to pay as much for all those wells. Water source heat pumps are typically zone-based water-cooled DX systems that share a common condenser water loop. Now, these actually a lot of times are above the ceiling in spaces. Then they'll have ventilation brought directly to them. So generally these are coupled with a dedicated outdoor air system, which is a very efficient way of providing ventilation to your zones. This allows for an increased efficiency through greater zone control, higher water-cooled efficiencies, and there's heat sharing through that common condenser water loop. Now, depending on how these are set up, you could run into that local recirculation limitation Jeremy talked about. They do have their own individual filters and compressors that would be above the ceiling or in the mechanical room, wherever they're at, and they could serve multiple spaces. But if they were coupled to a single room, you would potentially run into that local recirculation limitation. Now, VRF systems are something we don't see a whole lot in healthcare applications, but there's not really necessarily any code requirement that precludes them from it. There's a lot of similarities between VRF systems and water source heat pump systems and the way that they're applied. Both of them are somewhat zone-based systems where you could serve one individual space or maybe a cluster of spaces with a single system. You can see the picture really depicts that each individual space here is served by one VRF indoor unit, but they do make ducted units that could be used to serve multiples of those at the same time. Rather than having a common condenser water loop the way water source heat pumps do, VRF systems have a common refrigerant network that connects multiple indoor units to a single condensing unit that houses this single compressor that serves multiple indoor units. So now you have a relationship of many indoor units to a single outdoor unit, where then they can share load and also share heat recovery. So heat recovery VRF systems allow for simultaneous heating and cooling of indoor units on the same network as depicted here, where you can see that the south side, all of the units are in heating mode, whereas the north side, all of them are in cooling mode, and they're all on that one single refrigerant network. And now, when you're in this heat recovery mode with simultaneous heating and cooling, the great part that helps with efficiency is that you only have to pay for one of them. So whatever the predominant load is, you pay for the compressor energy for that, and then there should be enough potentially recovered heat, hot gas coming off of those evaporators, to be able to divert to the zones that need heating. So you're really only having to pay for that once. So that's a big efficiency gain. Now, the issue with VRF systems is they require a lot more refrigerant, because now instead of running water, we're running refrigerant lines all throughout the building. This makes them, according to what ASHRAE Standard 15 describes, as a high-risk system. That means that now we have to look at complying with ASHRAE 15, which gives us a refrigerant concentration limit that is calculated based on if this entire system were to have a leak in the smallest occupied room and were to evacuate the whole system. Now, that applies to all occupancies, but the part that makes it particularly difficult for healthcare is ASHRAE Standard 15 states that institutional occupancies have basically half the limit. So that leads you to having smaller refrigerant networks, meaning more outdoor units, and so it does cause issues. Also, you would have the local recirculation limitation Jeremy mentioned, and so a lot of times we see these in administrative areas or something like that, or maybe some sort of other occupancy within the hospital, or maybe an outpatient clinic more commonly than inpatient.
Heat recovery chillers have a lot of synergy with hospitals. We've already mentioned the term simultaneous heating and cooling several times. It's almost unavoidable in a hospital because you have code minimum air change rates that may be different than what it actually takes to heat and cool a building. So there will still be plenty of times during the seasons where you're going to have simultaneous heating and cooling. So what a heat recovery chiller does is, instead of a water-cooled chiller that rejects its heat to a cooling tower, this rejects its heat to the heating system that you're already using for your facility. So you still have chillers and boilers, and they still serve their portion of the load, but the heat recovery chiller allows you to bridge that gap and capture that waste heat that would normally go to the atmosphere at a cooling tower and send it into to your heating system. So you'll still have cooling loads like you see on the left for air handling units, radiant systems, chill beams, fan cool units, things like that. And you'll still have heating sources on the other side for other chill beams, for air handling units, for any of your heating coils for your radiant loads, and they will happen at the same time. So you're running your chillers and the boilers at the same time, but you're able to capture that overlap. So there's a lot of synergy, and you see them a lot in healthcare facilities for that reason.
Cogeneration, similar idea to what Jeremy was talking about with heat recovery chillers, except now we're using a generator to generate electricity, and then we're capturing the waste heat off of that to reduce all of those reheat loads from our potential VAV or even constant volume systems. The viability of these systems is based on something called the spark gap, which has to do with the gap between the gas rate and the electricity rate. So you want to be able to use cheap gas to produce expensive electricity, and then make free heat. These are oftentimes coupled with a absorption chiller. Then it's referred to as trigeneration.
I'm not going to talk much about active chill beams here because we have a whole deep dive session on it in a few minutes. But generally, instead of what you would see in a constant volume or variable volume system, you're only sending the ventilation load to the room. You're only conditioning at a central air handler, the central ventilation load, and you're sending that to the space, and then doing the cooling and the heating locally. The main benefit of this is that it's much what would I want to say? It's much easier to transfer heating and cooling by water than by air. It's significantly more efficient way to do that, both in energy efficiency and in space requirements above the ceiling. If all you have to send is chilled water and a hot water pipe to a room, it takes up a lot less space than sending an entire supply and return duct to that room. But we'll talk about this a little in more detail in a minute.
Just like Jeremy said, I'm not going to go into super deep detail on this because this is what my case study is talking about. But dual pass air handling units are pretty self-explanatory. You're basically separating your cooling coil into having one for the return air versus the outdoor air. So then we've got a little better control. And I'll describe that a little bit further in the case study. So we've got this HVAC comparison chart to give you an idea of sort of relative to each of these systems we talked about, how they rate with one another from a first cost, energy efficiency, maintenance, and applicability to healthcare, to really give you a high level comparison of them side by side.
It's important to note that, one of the main takeaways from this chart is you can see that none of these systems are green across the board. None of them are the perfect system. It will depend on the parameters of your owner, the comfort level of your owner, your local jurisdictions, and the makeup of your building, what might be most applicable for you. And it's subjective. We discussed it and came up with this. It's not hard and fast, but it just gives you an idea of what we've seen. The last two columns on the chart, patient satisfaction and infection risk, we said that those are neutral if they're operating correctly. There's nothing inherently less safe about any of these systems if they're working correctly, and they're all able to take care of the load in the room and patient satisfaction if they're designed and they're operating correctly. When those might come into question is if one of these systems is too complicated or has too many failure points, or your hospital engineers operating the system are not sophisticated enough to maintain it and to deal with it. If it goes out of compliance, you could have patient satisfaction or infection risk problems in any system. But we wouldn't rank any of these higher or lower than any other in those parameters. So of the list that we just talked about, Corey and I have each selected one of those to do a deeper dive on. Mine will be active chilled beams. So we did a project that opened 5 years ago in Greensboro, North Carolina, the Moses Cone North Campus expansion, and it was one of the, if not the first, hospital in the country to have active chilled beams in the patient care areas. The project was about 200,000 square feet, almost 100 patient rooms, and we had active chilled beams in all of those rooms except for the isolation rooms because of ASHRAE 170, because of the prohibition for recirculation in those rooms. We've already seen these pictures, but just to reiterate, we compared a VAV baseline project with a chilled beam project as we were trying to get this system approved in the building. So instead of sending 6 air changes or more of cooling air to the room and then returning most of that, we instead just sent the two air changes of primary air to the chilled beam and then did the cooling locally at the room. I won't say too much about the air handler arrangement that we used, but since it's 100% outside air because we're only sending the outside air, the ventilation air to the space, we wanted to recover as much of the energy as possible from what would normally be a return but is now exhaust. So we have a flat plate heat exchanger as well as an energy recovery wheel to wring as much of the energy out of that before we send it out of the building. The other thing of note here is that in a traditional VAV system, we'd probably send the air out to the space at 52 degrees and saturated or something near that. In this system, we're able to send the air warmer and drier, which is another source of the energy efficiency of this system. Healthcare is a conservative industry for all the right reasons. They're taking care of patients first and every other consideration is second. So when new technologies come out or new systems get evaluated, there's resistance, and they're responsible to do that. Some of the resistance to this system was no one quite understood the first cost because there weren't 10 examples of it to judge from. There was a perception that introducing recirculation into a patient room would lead to an infection risk, so that was a concern. No one was certain how the temperature would control. The biggest one that we hear, though, is that you're putting a cooling coil in the room, it's going to rain on the patients. So that's something that we needed to wrap our heads around and to solve for. The biggest concern, though, is that there just wasn't precedent. There wasn't real-world data. So most of the rest of this presentation that I'm going to show you is data that we gathered because there was a lack of data. So we wanted to get that information out there. So from a first cost perspective, we drew half a floor as a VAV system and half a floor as a chilled beam system so that the contractor could price it and we can have some real information to help make the decision. So the chill beams themselves and the secondary chill water system it takes to feed them do have costs, but what we found in our comparison was that it's 32% less ductwork on the whole, and that reduction in ductwork almost exactly paid for the active chilled beam system. So it was very close to a cost neutral change. So that really wasn't a concern for us. And it's really only getting better as more and more contractors are comfortable with the system. You don't see cost escalation just due to a fear factor. One thing that I would say didn't work out as well as we had hoped was the maintenance and the lint buildup. So in every patient room you have linens, and those linens put off lint. And normally that builds up in your return air system. But because we have this chilled beam, and that's where the return air goes, there's lint buildup on the beam. So we worked with the manufacturers ahead of time, and we had proposed that it's probably every 2 or 3 years that you have to vacuum the beam. What we found in practice was it's probably every quarter that they need to vacuum the beam. And so the way it works is you can hinge down the cover plate inside the room to get access to the coil. And you can see this coil on the left has lint buildup. This was over a period of about maybe 6 months, and you can start to see lint buildup on the coil. That would have normally gone into your return air system, but it got caught here at the beam. But even after 6 months with this amount of lint, there was no performance degradation. It was just an issue. So they bought a HEPA vacuum, and they go in and they vacuum these beams about once a quarter. The entire process takes about 15 minutes from the time you go into the room, open the cover, vacuum the beam, close the cover, wipe everything down, and you're done in about 15 minutes. This is him checking the beam just to make sure there's no lint up above. The lessons learned are you really need to befriend your room schedule, or the maintenance staff really needs to befriend their room scheduler, because you can't say I want to clean room 1 at 8 o'clock on Monday and room 2 at 8:15. It depends on when the patients are there. So you need to understand when the rooms are occupied, understand when you can get in there, and keep track of what you've done, because you might do room 2, then room 27, all over the place. And you need to train multiple staff members because rooms are available at different times. They've experimented a little bit with linen standards. There are some linens that put off quite a bit of lint and some that don't. So if you have the system, it might be worth doing a little bit of research in that area. Temperature control. So this is an overhead map of the entire campus. The yellow area was the existing campus, and the blue area is the North Tower expansion that had the active chill beams. So there are 470 beds in the old hospital, and they are varying types of mechanical systems. There are some VAV systems, there are some fan coil units, there are some PTAC units at the window. There are all kinds of different systems. But out of those 470 beds, we studied both sets of rooms for a year after this project, and there were 1,400 complaints or so in the yellow portion, in the existing portion, and about 70 complaints in the North Tower with chilled beams. So if you convert it to complaints per room per year, there were about 3 complaints per room per year in the old hospital and less than 1 in the new hospital. And I would call that a 431% improvement. So I mean, you might look at this and say, wow, there are still 70 complaints, but in truth, hospital patients are uncomfortable because they're in the hospital. There are some patients you're never going to make happy. These are experts from the actual logs of complaints. There was a patient that was too cold at 90 degrees and a patient that was too hot at 70 degrees. If that's the situation you're dealing with, HVAC is not the problem. So I don't think the goal of getting complaints to 0 is a reasonable and achievable goal, but we certainly reduced it quite a bit. Condensation is another big concern, but it's not like the coil. The coil in the chilled beam is a cooling coil. It's not a condensing cooling coil. It's not designed for that. We're not sending 42-degree water to it. We're sending 57-degree water to it, and we're measuring the dew point in the room to make sure that we never approach it. So in 4.5 years or so of operation, there's been one instance of condensation, and that was when there was a failure in a sensor in the secondary chill water system that caused us to send too cold water out there. That was diagnosed pretty quickly and solved. So with the exception of that one event, there's been no condensation in these rooms. As long as your envelope is tight and no outside air gets into your rooms, the surface temperature of a chill beam is actually warmer than that of a VAV diffuser. So the VAV diffuser is more likely to condense. Infection prevention was another major concern. There are people that would say that introducing recirculation into a room increases the potential for infection, and infections are extremely expensive for a hospital. If someone's readmitted for an infection that they acquired in the hospital, every bit of that second stay is non-reimbursable and a complete loss for the hospital. So it's definitely something to be aware of. Multiple contributors to hospital-acquired infections. Most of them have to do with the actual occupants, the patients and the family and the staff even, and how often they wash their hands and how easily they have access to hand washing. There's really been no direct link established in any of the research between HVAC and infections, but because that perception is out there, we needed to study it. So Cone was nice enough to open up their infection data to us. So we studied a period of about a year before and about a year after with the same patient populations and tracked their infection rates. So these are the four metrics that Cone tracks: fusions, laminectomies, total hips, and total knees. And there are actual units on the left. We didn't put them on the chart because they didn't want us to publish the specifics. But in every single case, the infection rates went down in every one of these rooms. So I want to be as clear as possible. I'm in no way saying you should go install chilled beams as a means to reduce infections, but I am saying that the data that we have doesn't support the notion at all that active chilled beams or recirculation introduces an infection risk. The new facility was better in a lot of reasons. The HVAC system was better. They had better access to hand washing, lots of things like that. One aspect of this is in a VAV system or a constant volume system, you're taking air from every patient room with everything that's wrong with all of those patients, sending it back to an air handler, filtering it and cooling it, and sending it back. So what's in room 27 will go back to the air handler and end up in room 45. In a active chilled beam system, that recirculation keeps whatever that patient has contained within that room, so it prevents cross-contamination. So that could be part of why we're seeing a reduction in infection rates, but again, we're in no way taking credit for that. From an energy use perspective, we predicted that it would be about 30% better than the 90.1 baseline, and in actuality, when we measured it in the following year, the green line is almost exactly on point. So we did save a considerable amount of energy compared to the baseline. Most of this is what we've already talked about before. We would say that it's gaining a lot of popularity in the market. There has historically been a lack of data, but that's part of why we gathered all this data, is to try to get that information out there so that everyone can at least make an informed decision.
Awesome. Thanks, Jeremy. So my case study, a little less intensive than Jeremy's. He definitely got the cool system to talk about, but here, talking about Lee Health Point, a project that we did in Coconut Point, Estero, Florida. It is not an inpatient facility, but it does have ambulatory surgery centers, recovery care, freestanding ED. So it has a lot of those intensive spaces. In healthcare, and Jeremy's alluded to it in his a lot, that the number one energy user is heating. And a lot of that is driven from the reheat because of all of these maintained ventilation, primary and outdoor air changes from standard 170. So we're constantly having to cool air down just to be able to heat it back up in order to maintain comfort in those spaces. So when we're looking for energy efficiency in healthcare, we're really looking for ways to reduce that heating energy because it is the biggest piece of the pie here. One way is using active chill beams, as Jeremy has described, because they do reduce that significantly. But a way that you can do that with a standard VAV system or really even a constant volume system, is to employ a different type of air handling unit like a dual path unit, where now we've put a cooling coil separately in the return air path from the outdoor air path, and we can control those separately from one another. This is particularly useful in hot and humid climates because a lot of the latent load or humidity that we're trying to control in the space is coming from that hot, humid ventilation air that we're bringing in. So the ability to subcool that and dehumidify that separately from the return air path gives us a real advantage in being able to expand the supply air temperature reset scheme in our buildings. So a couple pro-con here, benefit, drawback. Like I said, these allow us to expand the supply air temperature reset. And what I mean by that is that when the zones that the air handler serves are satisfied or are all being overcooled, then we can begin to increase the leaving air temperature off of our coil so that then we can save both cooling energy and reheat energy at the space as long as we're maintaining the humidity. So we really get a double whammy there from an energy standpoint. Drawbacks, there is a little bit of an increased cost. You have an extra cooling coil. The air handler box is typically larger in order to accommodate that, so you may need more mechanical room space. And this actually works better when you have more smaller air handling units, and that's really just about having greater zone control, because you can only begin to do supply air temperature reset, even with a dual path unit, if all of the zones that unit's on are satisfied. So the more zones it serves, the more of them that have to be simultaneously satisfied in order for this sequence to begin. So just looking at a quick comparison here, single path unit, we're bringing in, just for even numbers, 1,000 CFM of total air, 30% of which is outdoor air. And I used, we're looking at this example specifically for this Lee Health Coconut Point project. So we're looking at, hot, humid Florida ventilation design air coming in at 92 degrees and 54% relative humidity. And, if we were looking at the evaporation design time, it would be even higher humidity, probably a little lower dry bulb there. So each of our zones, you'll notice, in order to maintain their 72-degree set point with 50% RH, each of them are having to reheat some portion of the air. You'll notice that basically in order to maintain room 1, we actually are supplying 68-degree air, and so we're having to reheat that from 55 to 68, and room 2 from 55 to 65. And, this is just a small simplified example of what's going on with this system. So then if instead we were to employ a dual path system, we actually, when we're starting to get into those part load situations where both my rooms are satisfied, they're both reheating, then I can still keep dehumidifying my outdoor air, wringing out all of that same moisture that we're doing, while then I begin to reset the return air coil to provide warmer air off of it. And that's especially useful as you see that some of the indoor humidity is going down, and that we're able to control that just with the ventilation portion. Then we're able to supply warmer air that is more dehumidified still than if we were to just reset a single path cooling coil, and that allows us to reduce the overall cooling, you can see, by half a ton at this specific example, while reducing the reheat at the zone significantly. That's okay. The end of my case study there.
Great. Well, thank you, Corey, and thank you, Jeremy, for that exceptional information. And now our presenters will answer questions about this topic. Please type your question into the Ask a Question box on your screen, typing the presenter's name before your question so that I know who should answer it. We'll get to as many questions as time allows. And additional information will be posted online at csemag.com, that's csemag.com, with the archived version of this webcast. As a reminder, you may earn one AIA CES approved learning unit for this event, and you need to pass a 10-question exam. To take the learning unit exam and to download your AIA CES certificate, use the Learning Unit Exam tab option at the top of your screen. The exam will open in a new browser window. You can complete the exam after the webcast. However, the link will break when the webcast signs off. The exam will be posted on the Consulting Specifying Engineer website with the on-demand version of this webcast. Now, before we get to the questions, we wanted to let you know about another opportunity to earn continuing education credits. On CFE EDU, an interactive educational platform, you can register for the course Data Center Air Handling Units, which you may take on demand. There are many, many other courses to choose from too. Click on the link on the downloadable PDF of these slides to get to any of these CFE EDU courses. All right, Corey and Jeremy, we're going to start with questions. Jeremy, I'm going to kick the first question to you. What are the best design practices in achieving room air pressurization in healthcare facilities?
Okay, there are a number of facets to that question. I think you would start with ASHRAE 170, which will define whether your room needs to be positive or negatively pressurized or has no requirement. Then you need to understand the leakage paths available. It's generally the door into, or the doors into and out of the room. Even a closed door has a crack area, which is the code term for it. Below the door, there's an air path below the door, and maybe even at the side of the door. If there's a double door, there's an air path at the bottom, and also an air path between the two doors. So you need to do a little bit of calculation on what the expected leakage path might be, and then there's a formula for it. It's the air quantity of the offset you need to maintain across that door in cubic feet per minute is 2,610 times the area of that crack volume times the square root of the differential pressure, and that is measured in inches of water. So 0.01 is kind of the target that you want to reach for. You might do it between 0.01 and 0.02 just so you're over it. So that all of that defines the offset that you want to maintain across a given door. But then to actually make that happen, so like in an operating room, for example, where you might have a code minimum of 20 air changes, but the load might require 30, and sometimes you want the air quantity to be able to vary and the room to stay positive. You also might have a night setbacks sequence where you might go down to 6 air changes at night. You want the room to stay positive in all of those scenarios. So the best way to do it in that case would be to have high precision air terminal units, like a Venturi valve or something like that, where you have a tracking pair of supply and return valves that go up and down together and maintain the same offset. If you have a room like a clean utility room that needs to stay positive, but it's a small load to begin with, you might just make that specific room constant volume and let the return air modulate with the system so that the room always stays positive. It'll change its positive and negative, but it'll always at least be positive. In a room that needs to be negative, like an isolation room, you would either make those constant volumes or have those supply and return connections tracked as well. We found that the high performance type valves perform a lot better than a blade damper valve in those cases. That's what I would say about that.
All right, thanks, Jeremy. Corey, the next question goes to you. What types of products or systems can reduce HVAC ventilation load in hospitals?
So this is something that comes up a lot and is a little bit of a typical confusion from what we can do in other commercial buildings using ASHRAE 62.1 versus the ventilation requirements that 170 imposes. Standard 170 is only a prescriptive based ventilation requirement. So there is no way to use any sort of air cleaning system to allow a reduction in that. Now, there's nothing that keeps you from employing such systems. I know that there are lots of healthcare facilities that do, but it doesn't allow you to reduce the amount of ventilation required to the system in the same way that you could with a commercial facility utilizing the indoor air quality procedure of ASHRAE 62.1. Now, there are other systems where you're not reducing the quantity of ventilation, such as a heat recovery wheel, maybe an enthalpy wheel, or a plate and frame heat exchanger like Jeremy mentioned they used, that you can actually, recover some heat or cool to provide pre-cooling or preheating of that ventilation air that is required via standard 170, but not a reduction in ventilation itself.
All right, very good. Jeremy, I'm going to kick this next question over to you, and it's a little long, so I'm happy to repeat any portion of it. Some jurisdictions do not allow for variable air volume systems in hospital patient care environments, particularly OSHPOD. So the first question is that correct? And then secondly, those VAV minimums must not be set below the values in ASHRAE 170. Is that correct?
Okay, so unfortunately, I can't really speak to California. I've never worked for OSHPOD. I've never worked in California, so this is likely a jurisdictional question as well. Most of my career has been in Texas and in North Carolina, and it's perfectly allowable in both of those jurisdictions. So I might do some research and follow up in the written portion of these questions. But for the second part of your question, what I think what you said is that it's not, if you set the minimum in a VAV system to the code minimum, there's not going to be much variation because the actual load in the room isn't going to be much over that. My experience has been different. If you're in San Diego, it's 72 degrees out time. There's all the time. There's no load in the room. It's about the same as the outside. But in a lot of climates, in northern climates and in southern climates where it's hot and cold outside, I have seen the load be significantly higher, especially in places like operating rooms. There's a lot of equipment in operating rooms, especially specialty operating rooms like a cardiovascular OR or a neuro OR. There's a lot of equipment in the room that would push if the minimum in an operating room is 20 air changes, the load-driven maximum might be 30 air changes or more if they have a complicated surgery type with a lot of occupants that are sweating and a lot of equipment buzzing. And in an ICU, there's a lot of equipment in there keeping that patient alive. So you really do need to check your loads to make sure what the maximum truly ought to be, because I have seen it be significantly higher than the code minimum. If you have a patient room or any rooms with significant glass exposure because they want nice views, that's another thing that can drive the load up. So I would not say that there's not a lot of variation in a VAV system. I have seen the opposite.
Okay, yeah, thanks for that clarification, Jeremy. Corey, it looks like we have time for one last question, and it goes to you. We're going to go back to ASHRAE 170. Does ASHRAE 170 essentially prohibit the use of variable refrigerant flow systems, so VRF systems, in patient care areas due to the requirement for having MERV 14 afterfilters downstream of the air handling units? Can you talk about that a little bit?
Sure. So this is an example of where that VRF systems are not specifically not allowed, in the same way that chill beams aren't specifically not allowed in spaces that require or not allowed to have local recirculation. But it is difficult to meet that requirement with a VRF system. I wouldn't say that it's completely impossible. You wouldn't be able to do it with a cassette type indoor unit, but you could potentially fit one of their concealed ducted units to try to do that, but you would have a reduction because of the increased static pressure, so there would be a negative effect on the performance from an airflow standpoint on those units. So yes and no. it does make it more difficult, impossible. I don't think so, but yeah, significantly discourages it.
All right, got it. Well, thank you. I would like to close by thanking our rock star speakers, Corey Duggan and Jeremy Jones, for sharing their extensive knowledge and understanding of HVAC systems in hospitals. I'd also like to extend a special thank you to our sponsors, Egis and Carnes Company, for supporting today's webcast. Now that we are just about done, we want to hear from you about what you thought about this education session. A short survey will pop up on your screen as soon as this webcast event ends. Please take a moment to complete it. We use this information to improve our webcasts. Finally, on behalf of Consulting Specifying Engineer and CFE Media, thanks for attending this webcast. This now concludes today's event. Thank you for joining us, and goodbye.